In 7.4, we're dealing with partial fractions. Partial fraction decomposition of a rational function, which is p of x over q of x, where q of x has non-repeated linear factors. Partial fraction decomposition of p of x over q of x, when q of x has non-repeated linear factors and the degree of p of x is less than the degree of q of x, is the following. You would have p of x over q of x is equal to a1 over a subscript 1x plus b1, and so on. So how do we go about this? Well, if we're given a rational expression with distinct linear factors in the denominator, we're going to decompose it. We're going to use a variable for the original numerators, usually a, b, or c, depending on the number of factors, placing each variable over a single factor. And for the purpose of this definition, we're going to use a subscript n for each numerator. Then we're going to multiply both sides of the equation by the common denominator to eliminate fractions. Number 3, we're going to expand the right side of the equation and collect like terms. And number 4, we're going to set coefficients of like terms from the left side of the equation equal to those on the right side to create a system of equations to solve for the numerators. So for example number 1, we're going to be decomposing a rational function with distinct linear factors. Decompose the given rational expression with the distinct linear factors. So we have 3x divided by x plus 2 times x minus 1. The first step we want to do is we're going to separate the denominator factors and give each numerator a symbol like a, b, or c. So our expression is 3x over x plus 2 times x minus 1, and we can write this now as a over x plus 2 plus b over x minus 1. Number 2, we're going to multiply both sides of the equation by the common denominator to eliminate the fractions. Well, the LCD is x plus 2 times x minus 1, so we're going to multiply both sides, or all 3 terms, by the LCD. If we multiply this first term by the LCD, it eliminates the denominator, so we get the resulting equation is 3x here equals, over here we can eliminate the x plus 2, what we have left is a times x minus 1, plus over here we can eliminate the x minus 1, so we have b times x plus 2. Now in step number 4, we want to expand the right side of the equation and collect like terms, meaning we're going to distribute a and distribute b. So the left side stays as 3x, we distribute the a and we distribute the b, we get ax minus a plus bx plus 2b. So now what we want to do is we're going to collect all the x terms and all the constant terms. So here we have ax and bx. So we're going to combine those as a plus b and then x. Then we have minus a plus 2b. And so then what we end up getting is the following equation. Now I add a 0 there for a specific reason. So when we start step number 5, because what they want us to do is set up a system of equations associating corresponding coefficients. So if you look on the left side of the equation, we have the coefficients for x, and the coefficients for x on the left side is 3, and the coefficients on the right side is a plus b. So that gives us equation 1, where we set a plus b, which is equal to 3. Now, then we have here we have 0. And over here we have minus a plus 2b because it doesn't have a variable term associated with it. So therefore we're going to set negative a plus 2b equal to 0. And now we have a system of equations to be able to solve for a and b. Now step 6, we're going to add the 2 equations and then solve for b. So equations 1 and 2, if we add them, we eliminate b. We get 3b equals 3, and therefore b is going to equal 1. Step 7, we're now going to substitute b is equal to 1 into one of the original equations in the system, so we can substitute it back into equation number 1. So we get a plus 1 equals 3. Subtract 1 to both sides, we get a is equal to 2. Now we're going to plug in a and b into the decomposition. And so therefore we're going to get 3x over x plus 2 times x minus 1 is going to equal 2 over x plus 2 plus 1 over x minus 1. And if I scroll back up, recall that a was the first numerator, b was the second numerator. And so what we got for a was 2, and what we got for b was 1. Now, there is another method to use to solve for a or b, and it's by considering the equation that resulted from eliminating the fractions and substituting a value for x that will make either a or b term equal to 0. So if we let x equals 1, 1 minus 1, the a term is going to become 0, and then we can simply solve for b. So if we plug in x to be 1, we get 3 times 1, which is 3. 1 minus 1 is 0, so 0 times a gives you 0. And then 1 plus 2 is going to give you 3 times b is 3b. So if we solve for b, we can see that b is equal to 1. And then we can either substitute b is equal to 1 into the equation and solve for a, or make the b term 0 by substituting x is equal to negative 2. So let's follow the same pattern we did in step 1. So we're going to let x equal negative 2 and solve for a. So we have 3 times negative 2, which is negative 6. Negative 2 minus 1 is negative 3 times a, which is negative 3a. Negative 2 plus 2 is 0, and 0 times b is 0. And now if we solve for a, we divide both sides by negative 3, and then we get 2. So then we're going to obtain the same values for a and b using either method. So the decompositions are the same using either method. Now, although this method is not seen very often in textbooks, we present it here as an alternative that may make some partial fraction decompositions easier. It is known as the Heaviside Method, named after Charles Heaviside, a pioneer in the study of electronics.